Good morning, folks. Jim Giacchetta here, Vidovation. Basically, we're going to look at some of the different challenges that 4K presents. If you're a broadcaster, you might be looking for higher resolution, or if you're a sports league, it may not be so much about resolution, but you might want higher frame rates for instant replay and things like that. So we'll touch on some of these subjects, and we'll share with you some of our future developments in the area of wireless and 4K video. So let me just jump in. So what's the problem we're dealing with? You know, we have this higher resolution video that's been thrown at us. Actually, there isn't so much video. There's a lot of displays that are out there. The manufacturers of the displays have been doing very well with their marketing, pushing 4K, getting people to buy a 4K display at Costco, but there's not a lot of content out there yet. So usually it's the other way around, or the content kind of lags behind the displays a little bit. And in this case, the consumer side has outled is out in front of the technology. There's also a divergence in the way the video is described. High definition video in the past, and excuse me, take a drink of water. High definition video in the past was described resolution-wise by a number of lines, 720p, 1080, and such. 4K now is describing the number of pixels horizontally instead of the number of lines vertically. So I think the marketing people at some of these display manufacturers have gotten hold of that, and the terminology now has kind of changed. And 4K is not the whole picture. You know, some of these scan rates are above 4K. Some are a little less. So we're kind of fudging some of the numbers here a little bit. So which adds to the confusion. You can see here in this graph, you see 1080p. Let me turn on my little laser. You know, it's a quarter of the size of a UHD or a 4K image. So we have to deal with 4 times the number of pixels, 4 times the resolution, 4 times the bandwidth, 4 times the throughput. So this adds to the challenges we face, whether it's through a coaxial distribution, fiber optic distribution, or wireless distribution. What we're going to concentrate today on is the wireless challenges with the distribution of 4K. In future webinars, we'll talk about 4K development in the area of fiber optics, 4K development in the areas of IP encoding and decoding. But today we're concentrating on wireless. So here's a quick little chart. I'm not going to read this all to you, but you can see here we have different horizontal and vertical resolutions. We're all kind of lumping this together into 4K. You can see some of them are a tad under 4,000 pixels horizontally. Some are a little over. We have different aspects ratios. You know, some are for television, some are for cinema. So it's already getting a little complicated, and we have a number of different scan rates, pixel horizontal and vertical pixel counts to deal with. But we're lumping it all together under the 4K umbrella. So Vidovation, we're most known for 60 gigahertz wireless video and Ethernet. We do have systems that use other frequencies, but our biggest claim to fame is building wireless in-net camera system for the National Hockey League. It's in use today, later today, during the Stanley Cup playoffs. They have been in use now. This is our 4th season in operation with 60 gigahertz uncompressed wireless video in a compact camera system. But we do other technologies. We do licensed bands, unlicensed bands, but we're going to concentrate on higher frequencies, 60 gigahertz and above today, which the higher frequencies lend themselves to higher bandwidths, higher throughput. So again, we're kind of looking at 60 gigahertz and above. So as I mentioned, 60 gig today gives us the ability for a 1080i 5994 or 60, or 720p 5994 or 60, or a 1.5 gigabit per second HD SDI signal. And this is commonplace for us. I mean, we do this all day long. This is a sample of one of our video wireless links. Here's an Ethernet link that we provide. And you can see 1.5 gigabit per second video or 1.25 gigabit per second bidirectional gigabit Ethernet. These systems today use relatively simple modulation schemes, on-off keying, or amplitude shift keying. It's just basically we have a carrier and we're turning it on and off, AM modulation or amplitude modulation. So it's pretty simple, pretty rudimentary. It helps keeps the costs lower if there's not a lot of modulation or a lot of encoding or decoding or complex modulation. It simplifies the electronics involved in the front end and the back end, in the front end of the transmitter and the back end of the receiver. So AM modulation, the presence or absence of a carrier wave is another way of looking at it. And because it's a simple system, it's typically 1 bit per symbol. So thinking of it like a computer, we have a bus that's only 1 bit wide. So we can only get 1 bit at a time through the system. Our future development to be able to get a higher order bandwidth or higher bandwidth up to 10 gigs or even 12 gigabits per second, we need more complex modulation, more complex encoding algorithms to achieve this. So, if we want to get a UHD 3840 by 1260 at 60 hertz, we're going to need a 10 gig pipe. And the way we can do that is through advanced modulation. So whether it's uncompressed 4K video or gigabit Ethernet or 10 gig Ethernet, 10 gig E, we're going to need a fatter pipe. And we can get more through the pipe if we use more sophisticated modulation schemes. And, we didn't invent this. It's just that we're applying state-of-the-art technology when it comes to modulation to 60 gigs. In the past, it wasn't necessary to add these more advanced modulation schemes. The cost of the products will probably go up as a result of this. These products haven't been released yet, so we haven't set pricing. But, it's understandable that a 10 gigabit per second link is going to cost a little bit more money than a 1 gigabit per second link. And you can see here we use quadrature phase shift keying, and you see here you have a phase and an amplitude. So you have this I and Q grid, and you have a vector, a certain amount of I and a certain amount of Q, and then there's a phase vector and an amplitude vector. So this particular quadrant right here, 1, 1, 1, 1, gives you negative 2 units of I and negative 2 units of Q with a certain phase. That gives you this symbol, and this symbol you can see here is 4 bits wide. So we've gone from a 1-bit bus to a 4-bit bus if we implement, in this particular example, 16 QAM. So you can see how we've quadrupled the throughput in our AM modulated system. So we've gone from a single bit to a single bit per symbol to 4, 8, or 16 bits per symbol, and that's in respect to respective to 16 QAM, 64 QAM, and 256 QAM. And by QAM we mean quadrature amplitude modulation or quadrature phase shift keying. So that's what this little chart depicts here. So you can see, and chipsets are available to do this. Again, it's not anything new. We've been doing this for years. We're just applying it to our 60 gig radios or 80 gig, 90 gig radios, and even 100 gigahertz radios. So this is how we're able to achieve higher bandwidth, higher throughput. So for those of you that don't know me, I went to NYU Polytech. That's my alma mater, and recently, while I was doing some research about developments in 10 gig and above, 10 gigabit per second and above transmission, I found some papers out there that NYU has been working on. They have a millimeter wave and a 5 gig wireless research department at NYU Polytech, and they've been doing some interesting developments. So they've been able to, in the lab and in the real world, they've done some real world demos. They've been able to push 10 gigabits per second on a 73 gigahertz carrier. So the technology is starting to come out. We have plans later this year to come out with some 60, 70, and 80 gigahertz solutions that will push upwards of 10 gigabits. Like any university, there's corporate sponsors. So NYU has been working with Nokia and National Instruments to develop some of this technology. They've been using some 2x2 MIMO antenna schemes, and they've also been using a single carrier null cycle prefix modulation. And the interesting thing about this is in our industry we've heard of COFDM or OFDM type modulations. You don't hear about SCSP modulation that often, and it does show some increased efficiencies in power consumption, as well as better dynamic range for the transmitted signal versus OFDM or COFDM. So there's some interesting research going on at NYU that we should keep an eye on. Battelle has also done some interesting work in the 100 gigahertz spectrum and above. They've actually filed a petition with the FCC that seems to not be meeting much opposition to operate either license-free or with a license in the 102 to the one just under 110 gigahertz spectrum. You can, if you Google Battelle and the FCC, you can see some of the public notices about this petition that they've put forth, and it looks like it's going to go through. For those of you that don't know, Battelle is a nonprofit engineering research entity. I'm not sure if they're affiliated with any universities. I think they kind of stand on their own. So they develop technology with the intention of licensing it to the commercial sector. So they're doing this research. So I think they're looking for investors or licensees to take this technology once it's been FCC approved and to commercialize it. And they've had some successful tests, 10 gigabits per second and above. I've seen some of this equipment. It's been at NAB in years past. Again, it's still in its infancy. It's not commercially available yet, but there have been some successful demos and some successful trials done with this technology. There have been some regulatory barriers above 100 gigahertz. It's encouraging that Battelle is leading the charge in this area. It serves all of us for us to petition to get the FCC to open up more spectrum for wireless communication, for video communication in particular. I'll show you on some of the slides coming up that there's been some German research where they've gone only short distances to date, but they've been able, if you can go a short distance, you can always scale that up, higher powered amplifiers, that sort of thing. But they've been able to push 100 gigabits per second on a 237 gigahertz carrier. So they've had some of the universities over in Germany have done some successful trials and research in this area. The Japanese put into operation a 10 gigabit per second Ethernet link operating at 120 gigahertz for the 2008 Beijing Olympics. And that was a successful commercial usage of 120 gigahertz radios. Here you can see the German institutions. We have the KIT, the Karlsruhe Institute of Technology, the Frohoff Institute of Applied Solid State Physics, and the University of Stuttgart. They successfully modulated some radios to operate 100 gigabits per second on a 237 gigahertz system. They actually modulated a laser on a photodiode to produce a near terahertz radiation. So it's a combination of lasers and photodetectors as the emitter or the exciter for this high frequency transmission. This is a nice slide. So it shows you a little pictorial of what NTT and Fuji television networks achieved for the Beijing Olympics, and this was quite a few years ago. So we've come a long way since then. Really, in this country, I mean, a system like this could probably go into operation today. It's just we really need the regulatory approval to operate at 120 gigahertz band. It's relatively easy to get an experimental license to do this type of testing, but does take some regulatory politicking to get your application approved and to get it get a specific channel or a new slice of spectrum approved for Ethernet use or video communication use. But it's encouraging that the technology is there. It's not just theoretical. It's not just experimental. That the commercial viability is there. Samsung has been very instrumental in promoting 60 gigahertz when it comes to short-range Wi-Fi. They've developed chipsets and have come up with some small form factor radios to push 3.6 gigabits per second and 577 megabits per second for mobile devices. Here's a statement from Samsung, that Samsung has successfully overcome the barriers to the commercialization of 60 gigahertz millimeter wave band Wi-Fi technology, and they look forward to commercializing this breakthrough technology. So a lot of us broadcast manufacturers, when we're on the bleeding edge, when things are in the experimental stages or in the early stages, a lot of the components are extremely expensive, and it makes it cost prohibitive. The fact that Samsung is commercializing the technology and the chipsets to achieve this just helps us in other areas, so that if we can build a a broadcast or HDSDI or gigabit Ethernet radio based on consumer chipsets, that helps bring the cost down. Because a company like Samsung, of course, will do a volume, which helps to lower the cost of the technology. So you can see here new and innovative changes await Samsung's next generation device, while new possibilities have been opened up for the future development of Wi-Fi technology. And this is from Kim Chang-yong, head of R&D at Samsung Electronics. Samsung has a big think tank where all their engineers kind of live in kind of like a university type environment. I've read some stories about it. There's a lot of innovation that comes out of this South Korean Samsung electronic R&D think tank. So this is encouraging that the likes of Samsung are promoting this technology. So, as some of you probably know, the 802.11ad standard does address 60 gigahertz Wi-Fi, but there's not a lot of implementation. Even though it's part of the 802.11ad spec, not a lot has been done with it, and it's encouraging that Samsung or someone is leading the charge, and I commend Samsung for being that player. So the chipsets will be made available for all of us to use. Samsung's been able to eliminate the co-channel interference. You know, if you have two channels operating in close proximity, a lot of times you have interference. The nice thing about 60 gigahertz, because it's a shorter wavelength, the beams are very narrow, but then, you know, they'll hit off of obstacles and obstructions, that sort of thing. And, you know, as I mentioned, you know, Samsung has been instrumental in making the leap from theoretical to practical, or from the R&D lab to the real world. They're making that leap already. And they've been able to get, you know, speeds, you know, 10 times faster than typical Wi-Fi, whether it's 2.4 gig or 5 gig. So again, this is real world. We'll probably see the next generation of cell phones starting to have this type of technology built into them, and again, this helps serve the greater needs that we have when it comes to wireless communications. You know, yeah, again, you know, we've talked about this all the time, that, you know, 60 gigahertz may not be applicable for all applications. 60 gigs is very directional. It doesn't go well through objects. It bounces off of objects. So in the case of the National Hockey League, you know, we have clear line of sight above the goal to a receiver in the ceiling. The goal can have some movement on its pylons, but if you're a camera operator and you're operating a small mobile camera, whether it's ENG or sports, you need to move around. A 60 gigahertz radio is probably not going to be the ideal solution for that. So probably a 2 gig or a 5 gig or licensed or unlicensed or a 7 gig radio probably would be a better choice for those applications. But Samsung has overcome some of these. There's a technique in wireless communication of beam steering or beam forming, and you through phase shifting you can make signals cancel each other or amplify each other. So with beam forming or beam steering, so say a mobile recipient is standing in a crowd, and he tries to make a connection to a local cell tower. What the cell tower will do, it will triangulate the signal using beam steering to make a little hotspot right around that person. There's some interesting white papers on this type of technology out there, but I don't want to get too deep into it. But through beam steering and waveform shaping, you can triangulate on a given mobile device or a given receiver or a recipient of data and amplify or put them in their own kind of little hotspot So it's very interesting technology, and Samsung is putting some of this technology into some of their mobile solutions. So you see here, they're calling it the world's first micro beam forming control technology. That's what Samsung is doing, and the system will optimize the communications in less than 1/3,000th of a second, in case there's any change in the environment. So in this scenario I describe in a crowded, I think I'm from New York, so I think at Times Square. So you're in Times Square, it's New Year's Eve, the ball's going to drop, you have thousands of subscribers, or you're at a sports venue and you want to upload your video or your image to Instagram. This type of technology can put you or that subscriber, that user, in their own little bubble or in their own little hotspot, and it's a means of getting the signal out. So it's exciting technology. It's very interesting. We can maybe do a follow-up webinar on some of this technology as it becomes more commercially available. So what is Vidovation's plans for all this? So currently we have on our timeline 10 gigabit per second solutions in the V band, as we call it. The FCC designates different bands. They have different names or different designations. 60 gig falls in the V band. So initially, we're going to come out with radios that will do up to 10 gigabit per second throughput, either for video or for IP Ethernet. We're strongly thinking that since the world is going more towards IP, an uncompressed 4 gig video link may not be what the industry wants, but we'll wait and see. The first challenge is to build the radios. Usually starts with the radios, and you work your way backwards to the IOs or the front end or the physical layer. That's the easier part. So the challenge is getting the 10 gig throughput, getting the bits through the pipe, getting the bits through the transmission link, and we have plans to do V band and E band. E band is the 70 gig and 80 gig bands. The parts are available, so it's not theoretical. We're putting systems together, we're testing systems, so the parts are here. Long term, we'd like to investigate what Battelle and what the Japanese and the Germans are doing in these higher bands, particularly between 100 and 150 gigahertz. We'd like to see what's happening up there. Having a higher order frequency gives you more bandwidth, so maybe we don't need the complex modulation and encoding techniques if the FCC opens these higher frequencies to us. The problem is that there's not a lot of components. The components that Battelle is building for their systems, and I'm sure the components that NTT and Fuji Television were using were kind of on the experimental side. So experimental to me usually means the parts are expensive or have limited availability. Output power requirements. We have available to us today power amplifiers in the V and the E bands, so we'll have to come up with amplifiers at these higher frequencies to pump out 10 milliwatts or more of power. There are amplifiers available to us today. The amplifiers need to be very linear. We need 1 watt power saturation and compression points of 1 dB at 27 watts or more. So again, it comes to getting enough power. Some of these shorter range tests that are done in the lab, that's great in the lab and in theoretical, in the lab. But in the real world, we need enough power to go a kilometer, 500 meters, a kilometer, several kilometers, 10, 20 kilometers. So we need to have amplifiers that will give us the power we need at some of these other bands or these other frequencies. So, we can combine different amplifiers together to get the power that we need. But it's not just crude amplification. We need amplifiers that don't have distortion or third order intercept issues or intermodulation issues. It's got to be clean signals. So if the signals are distorted during amplification, that limits our transmission capability. The availability, since everything is digital now, the availability of fast A to Ds, D to As, and FPGAs to do the modulation and the encoding, those are available today. But at the data rates that we need, they're expensive. So again, with volume, these costs will go down. And then, we've done some tests. 64 to 128 QAM is achievable for a 10 gigabit per second link, and in a carrier bandwidth of 5 gigs wide. So within the FCC standard, we can achieve this at 60, 70, and 80 gigs. We're looking at the feasibility of doing 512 QAM. Again, the higher order modulation, you lose your noise floor in your receiver or in your link budget. There always is a trade-off. That constellation chart that I had with all the dots on it. As the dots get closer together, noise will make the dots bleed together, and you lose distance, you lose fidelity, you lose link budget. So it's not like we're gaining this throughput for free. We still have to be careful and not over encode our signal. So we still want to experiment using up to 512 QAM to see if we can get more throughput. Another approach is to take several 1 gig Ethernet radios or modems, combine them together, take say 10 of them to make a 10 gig E. This requires some load balancing in the IP realm. It's non-ideal for video communications. You prefer the packets to all travel together through one pipe, but these systems have such low latency that if video packets were split apart and put over 10 different pipes that are virtually identically in phase and delay, I don't see a big problem with that, but typically you don't want to do that with video communications. So that's one approach that we can use lower cost components to combine, putting 10 pipes together to get one fatter 10 gig pipe. That's an approach we can take. Cross polarization is another possibility. If you cross polarize, you can cancel out any interference, and the acronym for that is XPIC, or cross polarization interference cancellation. But this adds to the complexity of the antenna system. It's more expensive. We're able to do 5 gigabits per second using this technique. So, here's another, I kind of said this already, but, the approach of taking multiple channels, N times gigabit Ethernet links or N times HDSDI links to push through more bandwidth. We're a lot of the 4K cameras, it'll be like a 4 3G HDSDI coaxial feeds or fiber optic feeds. So 3, 6, 9, 12, 3 gigabits per second times 4 paths gives us, 10 to 12 gigabits per second. So we can use a similar type technique when it comes to radios. Just put radios at different polarizations, radios at different frequencies, And by polarization, what we mean is, the radio waves will come out at 0 polarization or at 90. So the receiving antenna horn has isolation. One element will only see the 0 polarization wave as the wave comes at it this way. The other polarization element will see only the wave that way. So we can kind of co-locate 2 radio waves on the same frequency, or if we combine slightly different frequencies with polarization, we can get better channel isolation to co-locate or cooperate, multiple paths through a given link. So there's many different ways to do this. So this type of technology we expect to have out later, end of this summer. A single in, single out, full duplex gigabit, 10 gigabit link we expect to have out later this fall or later in the year. So the multi-channel approach will be the first to come out, and then having one big fat pipe with a higher order modulation schemes will be later this year or in the fall. And the XPIC solution with the polarization cancellation has a little bit. I said this earlier. The antenna becomes more complex, which adds to the cost. So we're not sure how viable that is. Also, in some metro areas, there can be, if the antenna element or the dish becomes too large, there can be fees associated, upwards of $500 per month per foot of aperture of your dish. So a lot of our products, you can see the devices themselves, the antenna elements are small on purpose. Microwave horn technology tends to be smaller, but has less gain. A parabolic dish tends to have more gain, but then it's larger, it's less aesthetic. Some building owners don't like having large ditches on their roofs. So, the more spectrum we can get from the FCC, obviously we can have higher data rates. The higher the frequency, the higher the data rates we can push through. Opening larger channels above 100 gigs. If we can get the FCC to approve a 10 gigahertz wide channel in the spectrum from 100 to 120 gigahertz, that would be ideal. Battelle, we commend them for leading the charge. As 5G data and 4K video, we're going to need 10 or 12 gigabits per second to push this through. So we do see a need out there for this type of technology. Whether it's more IP-based versus baseband video, our gut is telling us it's going to be more IP-based. You could run very low latency encoders, very high bit rate for 4K, still maintain good fidelity, and just have the flexibility of a more diverse IP link as opposed to a dedicated SDI link or 4K SDI link. So, we also see the merger of data and RF systems, RF over fiber. Still a lot of content is delivered to the home, via, cable operator, via RF, and we see that going away. We're doing a lot of IPTV projects. So video is being put more on a more traditional IP network. You look at companies like AT&T Uverse. They're delivering a true IPTV, triple play service to the home, video, internet, and television, all IP based. There's no RF over coax or RF over fiber. So this all leads to the demand for fatter pipes, higher bit rates, and in rural areas where you don't have access to a fiber or a telecom connection, high bit rate wireless really lends itself for these applications. What we see is the bottlenecks in any network is the first mile and the last mile. It's like, how do I get on the network and how do I get off the network? If you don't have a high bit rate telco, a POP or connection in your building, you might have to put one of these radios up on your roof and beam to an adjacent building in a metro area to get to that POP. So we see demand for this type of technology growing. We've also done projects where these higher frequency radios have extremely low latency on the order of microseconds for high frequency trading. We've sold them to commodities traders, stock traders that they'll set up shop across the street from the given exchange, and they don't want to go through a public telecom circuit where there could be latency. They want to make their trades. Everything is down to the millisecond. There's high-speed computers making these trades. So anything from wireless video cameras inside of a hockey net to getting your location or your facility on or off that network for that first mile or last mile, or if you're a high-frequency trader, anyone that needs to move high-speed data, high bit rate, very low latency, this technology is right for you. So there's been a lot of government support. A lot of technology that ends up in the commercial sector started out in the government or the military sector, and DARPA is a big proponent of high-speed data. So some of this technology is classified. Once it's been declassified, it trickles down into the commercial sector. So we should see more things coming out on the horizon as a result of some of the initiatives happening at DARPA. We can do this 100 gigabit per second over millimeter wave spectrum. DARPA is doing some work, and again, it's classified, so there's not a lot of details floating around, but we know they're doing work in these areas. Here's a little slide, just kind of shows you there's a million different FCC spectrum slides, but this is kind of like a reduced snapshot here. Where we're operating, you can see here, here's the 3 gig band. Microwaves usually, most people don't realize, it's 2 gigahertz and above, all the way up to about 300 gigs. So it's a pretty wide swath of spectrum. The microwave band and the millimeter wave is the 60 gig band. It's somewhere in here. So this is where we're operating. And then you get to visible light, infrared, ultraviolet, X-rays, and gamma. So we're still within this 100 gigahertz, 120 gigahertz. We're still within the microwave band. It's quite a large band that we refer to as the microwave band that we operate in. So just like that slide gives you kind of an overview of the whole spectral band that we deal with. So as we mentioned, my Los Angeles Kings didn't make it into the playoffs this year, but my New York Rangers are struggling through, and this is one of my favorite shots. This is a shot during, I think this was 2 years ago. 2012, 3 years ago, when the Kings first got into the Stanley Cup final, and Jonathan Quick is stretching in the goal. This is a view from our camera, a live HD SDI 720p 5994 video coming out of the innet, coming out of the goal, coming out of our wireless camera system. So not everyone needs a hockey goal camera, but whatever your application might be, we set up a 60 gigahertz link through one of our partner integrators, the Fiber Group, put in a 60 gig link for the Carolina Panthers, the NFL. They needed to pipe video to a studio about a kilometer away or less than a kilometer away, and they were able to beam video reliably from the venue, from the top of the bowl to a studio a few blocks away. And it's the same story, you know. It's that first mile where you don't have connectivity. So they didn't feel like spending the money to dig up the street and to run a fiber. And a lot of our systems, I like to call them fibers that go through the air. You know, it's like a wireless fiber. They're that reliable. So, you know, it's really, you know, when you don't have access to a cable or a fiber, or that first mile and last mile bottleneck, that's really where we can help you. And, you know, the applications are infinite. You know, we can do, we've done military applications, sports, broadcast, Pro AV, cellular backhaul. Yeah, a lot of this technology is used to get the signal from a local cell site back to the central office is a common application. So, you know, we can support uncompressed HD SDI, 4K SDI is coming, ASI, and 10 gigabit, you know, 1 gig Ethernet and 10 gig Ethernet is on the horizon. And typical system in the 60 gig spectrum, it can go up to about 1 kilometer. If we do a 70 or 80 gig radio, we can go much farther. Those bands have a little bit of licensing. There is an annual usage fee for those bands. But, you know, licensing is not a bad thing. What that does is the FCC will mandate that, you know, you own the spectrum from this mountaintop to that mountaintop, or from this building to that building, and no one can put a radio next to your radio operating on that frequency. So sometimes it's worth paying that small annual fee for that peace of mind. 60 gigahertz is unlicensed, and you can put radios in close proximity to each other because the band is so narrow. But if you are going from the same pole, you know, the same rooftop to the other rooftop, and you're on the same tower, you might need to coordinate, you know, what frequencies or what polarizations you're using. So again, lightly licensed, as we call it, is not always a bad thing. But whatever your application is, we can help you pick the right technology for your application. So again, you know, support for 4K, 3G, dual link, dual channel type wireless systems. Thanks very much, everyone out there, and have a great Memorial Day weekend. And we'd love to hear from you soon. Thank you. Bye-bye.